Your network is a bit stressed. Your network has mission-critical data traffic moving through it. Your network has kind of clunky, big bandwidth downloading happening. Your network has mission-critical voice traffic that is trying to get through. Your network has really bandwidth and resource-intensive video traffic. If you don't have quality of service in your network infrastructure and you have the forms of traffic that I just described, you are most likely in very big trouble. We're going to take a look at the exciting world of quality of service. We're going to see the major approaches that you could take to this subject, and we'll analyze one of those approaches in great detail. It's called the differentiated services approach, and it is the common sense, scalable, awesome way in which to engage in quality of service in your enterprise. Unfortunately, it's quite complex, and that's why I am so glad you have found this particular live lesson. It's time now for me to talk about my absolute favorite topic in networking. That is quality of service, QoS. Let's go ahead and examine this complex topic in some pretty good measure of detail so that you feel very comfortable with it in your Network Plus exam environment. First up, when it comes to quality of service, we need to realize that we are talking about what the large vendors often refer to as a converged network. What do we mean by a converged network that's going to need quality of service? Well, the converged network means that it carries multiple forms of traffic. Gone are the days where the network just carries data traffic. The network may be carrying data traffic alongside with voice traffic, alongside with video traffic, and that's what we mean by converged. Many forms of traffic converging on this one network in order to form the converged network of today that we're so excited about. By the way, you might think, well, if converging these different forms of traffic onto the network are so problematic, why do we even do it? The answer is we can save quite a bit of money when we take these various traffic forms and converge them onto a single network, because now the support personnel is that one body of support personnel now that knows how to maintain that converged network. In simpler terms, we're not going to need specialized staff for the voice network, the data network, and a separate video network. We can go ahead and converge that staff together in order to handle this new network. Now, you see, quality of service, the performance of these networks, it wasn't that big a deal when they were all separated. But the minute you put these networks on the same network, and there is what we call contention for the network by these various traffic forms, we have a big challenge. Not only is the contention a big issue, but realize that not all traffic is created equal, is it? We have data traffic that is kind of, the run-of-the-mill data traffic is bursty in nature, and it's pretty tolerant of things like delay and maybe even a little bit of packet loss, thanks to things like transmission control protocol. But voice traffic is going to be extremely sensitive to things like delays or packet loss. So not all of the traffic is created equal, and that's why quality of service becomes a big, big issue. Here, just a reminder how voice is going to be very intolerant of jitter and packet loss. What in the world is jitter? It sounds like something that I have an issue with when I've had way too many cups of coffee before one of these videos. But what jitter refers to is variations in delay. You see, voice over IP phone equipment can handle a consistent, predictable delay just fine. The real big enemy of this voice traffic is when the delay is not predictable. When there are huge variations in the delay, we tend to have problems. So what we need is a managed unfairness. And that is my favorite descriptive term for quality of service. We're going to be unfair to certain traffic forms over other traffic forms, but we're going to manage this particular unfairness. So when we converge, there are some major issues that we run into. The contention, the competition for bandwidth, causing bandwidth shortages. And I'll tell you, when you start putting a lot of video over the network, like this particular lesson that we're viewing, it gets pretty resource intensive. The delays end-to-end, the predictable delay, and the unpredictable delay, the jitter, and also packet loss, all are enemies in that converged network that we use quality of service to help fix. Quality of service, again, is that managed unfairness. And to be more granular in our definition, to be more precise in our definition, we know it's providing a nice, predictable performance to particular traffic classes. We want our voice to get a predictable performance. We want our video to have a predictable performance. And we measure the performance in well-known, measurable, quantifiable parameters like bits per second in the bandwidth and like microseconds. And we really measure these things using predictable measurements. Another common measurement is round trip time. How long does it take the packet to leave the source, get to a destination, and then return, for instance? What you do when you are working with QoS in your environment is you go ahead and you figure out what types of traffic that you're using in your converged networks, and then you group those traffic categories that are similar, those traffic types that are similar, into categories. We can have voice. We can have control packets for voice. We can have video. We can have normal data like downloads. We could have data gaming traffic. We could have data that's for e-commerce. It's typical that we come up with about 8 to 10 different overall categories that we put all of our traffic in. And then what we do is we define the QoS settings that would be perfect for each of those different categories. And this is how we go about creating a QoS policy that works brilliantly for our organization. Now, there are 3 overall models for your QoS implementation. When you look at your organization, you can say, you know what I'm going to do about QoS? Nothing. And that's called best effort. Or you could say, we're going to take an integrated services approach. As you can see here, that is commonly abbreviated INT-serve. Or we could take a differentiated services approach. And as you can see here, that is abbreviated diff-serve. So we have our best effort, INT-serve, and diff-serve are 3 overall approaches that we can take to quality of service. Let's study each of these overall approaches or models in greater detail. First, best effort. With best effort, we're doing nothing. Okay, what we're really going to do, if we're going to use the best effort approach, though, is we're going to what's called over-provision. We're going to look at our video traffic and figure out our video traffic needs 2 megabits per second, and we're going to give it 10. We're going to look at our voice traffic, realize it needs 1 megabit per second, and give it 10. We're going to look at our data traffic, realize it needs 20 megabits per second, and give it 100. We are going to make sure we are over-provisioned everywhere, and now we don't have to worry about quality of service. You see, quality of service is only going to be a concern when we have those contentions and packet loss and jitter and all those things that come with the converged network typically. The interfaces won't engage in any kind of congestion management type techniques. Instead, the interfaces will just take the first packets that arrive and send them out first. It's a first in, first out approach. This is certainly easy to do, but why don't we see this done a lot? Money, money, money. That's right. Think about how inefficient it is from a resource perspective for us to be over-provisioning all of that bandwidth. There's nothing worse than wasted bandwidth, folks. Well, I suppose there's a lot of things that are worse than that, but you get my point. The integrated services approach. In the classic documents on quality of service, you'll see this abbreviated, or you'll see it referred to as hard QoS. Why do we call the integrated services hard QoS? Because we're going to be using a cleverly named protocol, the Resource Reservation Protocol, or RSVP. If you invite me to your Super Bowl party, I'm going to have to RSVP so that you have enough soda pop and Doritos for me to enjoy as I watch the game. This RSVP is a phoning ahead to make sure there's enough resources. This is exactly how this hard QoS, or integrated services approach, functions. The devices will communicate with RSVP, and they will ensure that there are adequate resources like bandwidth and things of that nature reserved for the communications. Wow, pretty cool. Can you think of any problem with this? I can. We are adding a whole bunch of overhead here, aren't we, in the whole RSVP process itself? And perhaps a much bigger issue is the scalability of this. How easy is this to manage, especially if we're partnering with a whole bunch of other organizations and networks? We've all got to be on the same playbook, and I guess that's another Super Bowl reference there. We've really all got to be on the same page in order to make this work. We've got to make sure that all of our devices are properly configured to do this hard QoS, this RSVP type of communication and process. So it sounds incredibly awesome in theory, but when we start looking at this integrated services approach, we realize just how tough it is to pull off. So the ultimate approach that is used today for quality of service by most organizations, it is overwhelmingly the most popular approach, is the differentiated services approach, the DiffServ approach. The problem with it is it's very complex for you as an administrator, but the great news is it is very scalable. In other words, once everybody learns how to do this, it's guaranteed to work as we move from equipment to equipment. What we do is we classify particular forms of traffic, like voice over IP. We put that in a voice over IP classification. We then mark at layer 2 of the OSI model and layer 3 of the OSI model, we mark that traffic as voice, and then we use tools to manage congestion on interfaces when it happens, to avoid congestion on interfaces altogether, to do like shaping and policing, slowing down the traffic by buffering it or dropping excess traffic in the case of policing. And we have link efficiency mechanisms like compression and link fragmentation and interleaving to help with quality of service as well. So you can see it's quite complex. We end up doing a whole bunch of different steps, classifying and marking and managing congestion and avoiding congestion and all of these as part of this overall differentiated services approach. But boy, oh boy, it is worth the effort, because when we pick up that voice over IP phone, no matter who we're calling, we have a perfectly crystal clear conversation thanks to all of these mechanisms working together. Now, I thought I would show you just a little sample of what this would look like on a network device when we go to configure it. Hey, take a quick peek at my Facebook page there. That's pretty funny. So let's go to a Cisco device. Here we have a router, and we'll go to this Cisco router and we'll take a look at the process for some simple quality of service. On a Cisco router, we can classify traffic in what we call class maps. Pretty cool. We go in and we name a class map like voice, and we distinguish on the router what packets should go in there. Now, it turns out that they make it really easy for us on a Cisco router these days, thanks to a special capability called network-based application recognition. Network-based application recognition allows us to go in and literally say, match particular traffic. We can say match protocol, and we can say real-time protocol for audio, for instance. So this is dynamically looking at the traffic and finding that real-time RTP. Oh, let me come up with it. It's the real-time protocol, I think. Yeah. Real-time protocol. I think that's it. Anyways, this is the matching that we can do for voice. The router is literally able to recognize the voice traffic. How cool. And now we have a bucket. I like to consider this class map as a bucket on the router where the voice packets are going to be poured into. Now, the next step of this, that we have the voice packets going into the voice bucket, is we create what's called a policy map. The policy map gets a name. I'll call mine, let's Mark. And what we do in here is we reference the classes. In our case, we'll reference our voice class, and we can set markings on the packets. For example, voice, we mark with expedited forwarding, or EF marking, so that devices will treat the voice traffic in a special way. The third step of this is to simply apply it to a particular interface. So we say interface FA0/0, for instance, and we say service policy. We reference the mark policy we created, and we say what direction. Actually, I think we have to say the direction first. Let's see. Service policy output, and then we can say like mark. And so there you have it. Here's a look at the configuration, a little snippet of quality of service on one of these Cisco devices. We go ahead and create a class map which matches on particular traffic. We create a policy map that does something to that traffic. In our example, we marked it as voice traffic. And then we assign this in a particular direction to a particular interface. We saw here on the Cisco router how we were doing differentiated services. In our particular example, we demonstrated classification and marking being done on a Cisco router. So now you get a sense for that, folks. And I hope you've enjoyed this presentation on one of the most interesting and certainly one of the most complex topics that you can get into with networking. It's quality of service.